Principal component analysis, PCA, is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. The number of distinct principal components is equal to the smaller of the number of original variables or the number of observations minus 1. This transformation is defined in such a way that the first principal component has the largest possible variance, that is, accounts for as much of the variability in the data as possible, and each succeeding component in turn has the highest variance possible under the constraint that it is orthogonal to the preceding components. The resulting vectors are an uncorrelated orthogonal basis set. PCA is sensitive to the relative scaling of the original variables. PCA was invented in 1901 by Carl Pearson, as an analog of the principal axis theorem in mechanics. It was later independently developed and named by Harold Hotelling in the 1930s. Depending on the field of application, it is also named the discrete Karhunen-Loewe transform, KLT, in signal processing, the Hotelling transform in multivariate quality control, proper orthogonal decomposition, POD, in mechanical engineering, singular value decomposition, SVD, of X, Golub and Van Loan, 1983, eigenvalue decomposition, EVD, of XTX in linear algebra, factor analysis. For a discussion of the differences between PCA and factor analysis, see CH7 of Eckart-Young theorem, Harman. 1960, or Schmidt-Mirsky theorem in psychometrics, empirical orthogonal functions, EOF, in meteorological science, empirical eigenfunction decomposition, Surovic, 1987, empirical component analysis, Lorentz, 1956, quasi-harmonic modes, Brooks et al., 1988, spectral decomposition in noise and vibration, and empirical modal analysis in structural dynamics. PCA is mostly used as a tool in exploratory data analysis and for making predictive models. It's often used to visualize genetic distance and relatedness between populations. PCA can be done by eigenvalue decomposition of a data covariance, or correlation, matrix or singular value decomposition of a data matrix, usually after mean centering, and normalizing or using z-scores, the data matrix for each attribute. The results of a PCA are usually discussed in terms of component scores, sometimes called factor scores, the transformed variable values corresponding to a particular data point, and loadings, the weight by which each standardized original variable should be multiplied to get the component score. PCA is the simplest of the true eigenvector-based multivariate analyses. Often, its operation can be thought of as revealing the internal structure of the data in a way that best explains the variance in the data. If a multivariate dataset is visualized as a set of coordinates in a high-dimensional data space, one axis per variable, PCA can supply the user with a lower-dimensional picture, a projection of this object when viewed from its most informative viewpoint. This is done by using only the first few principal components so that the dimensionality of the transformed data is reduced.
Please subscribe and thanks for watching.